guys, welcome to our next theory video. Today we're going to be having a look at magnetic fields. As you can see, I'm trying something a little bit new and I am now appearing on the video, so we'll see how that goes. So magnetic fields is following on from our study of electric fields, and hopefully it'll be a lot easier to understand because magnetic fields are something we've seen a lot, and we can play with them and touch them, and it tends to be a lot easier to deal with when we're talking about magnetic fields rather than something that we can't really see like an electric field. So hopefully that will make it easier. So we've all been looking at charges a fair bit recently, and all charges we know have an electric field associated with them. So that's what we've been studying for the past few weeks. Now, when these charges are moving, so any single moving charge, it actually creates a little magnetic field around that charge. So any charge that's still has no magnetic field, but anything that's actually moving or moving through a wire or any form of a current, or even a moving single charge, actually has a little magnetic field that gets made around it. So in the picture here, we have here we go. We've got a little wire, and we can see that the current, or the I, is going down, and then around the outside it's going to be creating a magnetic field because we have moving charges going through the wire, and they're all going to be creating a magnetic field. If we have a look at something familiar like a bar magnet, we've got what's called magnetic field lines, so very similar to our electric field lines, that you may have even done a prac about it in junior years, where we have a look at iron filings and check out the pictures that are made, and we'll probably have a go at that again if you haven't tried that one. We've got the direction of the field lines are going from the north end to the south end. Okay, so when we're drawing field lines for magnets, we start at the top, so north end, and we go to the south pole. So they say that the field at any point is directed at a tangent to the field at the point. And what that actually means, if you can see here, it just means if I was having to know what direction we were, the tangent to this line would be going straight. Here it'd be going, sort of down, where am I putting on the screen, there, that way, and it's at a tangent to whatever direction that line is actually being drawn. Now, this fancy sentence, the magnitude of the field at any point is represented by the number of field lines crossing a unit area. What that actually means is density. So the same as we were drawing for our electric field. If there's more lines, it's closer together, we've got a stronger field. So that's all that means. If we were drawing a bar magnet, magnetic field is a vector, so we need to represent it by a magnitude and also a direction. So the field lines that we had before going around the bar magnet, they're actually lines of force, so how much force is going to be acting on another magnet or another particle or something being put in that field. Now, the direction, we can tell the direction if we imagine, just like we had our positive test charge in an electric field, this time we're going to have a really small north pole of a dipole. It's like a mini tiny middle magnet, and we're worried about the north end, and we're worried about what would happen to that north end of a magnet, which direction would it get pushed or pulled, and we can determine the direction of the field because of that. As I was saying before, the field lines, when they're closer together, means it's a stronger magnetic field. So in the middle here, we've got a weaker field. There's only 3 going through that area, and we have the same area over here on the right, and it actually has 1, 2, 3, 4, 5, 6 lines going through it. So same area, more lines equals stronger field. Now we get to talk about something that we should all be familiar with, which is the Earth. And we know that the Earth has a North Pole and a South Pole. And we also know that we've probably heard of magnetic poles, and probably all seen a compass before. So here's where it gets a little bit interesting. So the Earth's magnetic pole and geographical poles do not coincide. So the North Pole, as you can see here, the North geographical pole is very different to where we would assume the North magnetic pole to be. It's off slightly. They're not connected, I guess. So the North geographic pole has no bearing on the North magnetic pole. They're actually in different spots. And if we have a look at this diagram here, it seems to be wrong, because I just said before that the field lines go from north to south. And that doesn't seem to be what's happening in this diagram. So we have to think about, well, why is that? And I just said that before, if we are trying to find the direction of a field, we should place our positive, or our north end of our little magnet anywhere in that field and see which end our north pole of the magnet goes. So if we placed our little north magnet at any point in that field, and just think of, use a compass, alright? So the north end of a compass is basically a little magnet, and the line or the little stick on the compass is our little magnet. And if we're going to point that anywhere, we're turning our little compass around, it's always going to point north. And so basically that north needle is pointing to the north geographical pole, which, you know, it means that the north pole of the needle is actually attracted to the south magnetic pole, which is located at the top of the Earth. Alright, which is essentially saying that our north magnetic pole is on the bottom, and our south magnetic pole is at the top. So it's backwards, which, you know, it sounds really funny. So yeah, go back to that one. So it's just saying here that remember that the direction of the magnetic field at any point is the direction of the force on the north pole of a compass needle placed at that point. So the north end of a compass needle is going to be attracted to the south magnetic pole, which just happens to be at the top. Alright, so the next part we're going to chat about is what this means for current. Because we're still following on from electric fields and electric current, and seeing what happens there. So the first thing is conventional current. So we've really sort of been studying current for about 200 years, since people discovered electricity and we started working with it and experimenting with it. And they use what's called conventional current. And conventional current is defined as the motion of a positive, or the positive flow of, the flow of positive charges, shall we say. Now, electrons were only discovered about 100 years ago. So all of these theories about current and electricity will all come up with pre-electron theory, basically. So we didn't really know that what was inside a flowing the flowing current was made up of electrons at the time. So they just decided to call it something. So they called it the positive flow of charge. We now know that actually electrons travel in the opposite direction to the current that's indicated, but we don't really seem to care. It's called conventional current. So when we say that the current is going this way, it actually means the conventional current, and if we're not talking about the flow of electrons, we just worry about conventional current. Now, we're talking about moving charges actually creating a magnetic field. So if we've got a current, it means that charges are moving inside that wire, and we're going to get a magnetic field happening around the wire that's carrying the current. Now, we can draw this quite easily, and we're going to have lots of practice at drawing it. But basically, when we're drawing it, it's represented by concentric circles that are centered in the wire. And one of the conventions that we use, that a current going into a page is represented by a cross, and out of the page is directed by a dot. And the way I like to remember it is thinking about an arrow. Okay, and an arrow, you've got a pointy end on one end, and then you've got the feathery part, I guess, I'm sure it has a proper name, at the back. And so if the arrow is coming out of the page, all you would see would be the tip of the arrow coming at you, which would be looking like a dot. So that makes me remember that the current's coming out of the page. And if the current's going into the page, all you would see would be the back of the arrow, or the little cross-shaped feathers. I hope that helps you remember. It works for me. It might not work for you, but a current going into the page is a cross, and out of the page is a dot. Here we have an example. So here we got our arrow gone into the page, so we can see the little feather part, and then we have a current coming out of the page, which is our dot or arrowhead coming at us. And this is what it looks like if we do it around a wire. So here again we have I, which is our current going down the wire, and around the outside we've got our concentric circles that are wrapped around the wire. So conventional current would go down the wire, and if we're talking about the flow of electrons, electrons would actually be going up the wire. Now there is a way that we can figure out what the direction of the circles going around the outside of the wire is, and this is where we get our first physics gangster sign. It's the right hand curl rule. So basically you have to give like a thumbs up, and if you see my hand, it curls around, trying to get a good view there somewhere. Alright, and basically if you point your thumb in the direction of the wire, the curl of your fingers represent, like the way your fingers are pointing, will be the arrows. Alright, so if you try holding your thumb up to the page and follow the current with your thumb, and then you'll see, if you wrap your hands in the same way that the little picture has, that your fingers should be pointing in the same direction as the arrowheads. And again, the one on the right hand side, if our current is going, I'm going to be backwards because of this webcam. Alright, your thumb's going this way and your fingers are pointing down, it's going to be exactly the same as the little picture there. Yours won't be as backwards as mine because mine is obviously in the camera. We can also use our right hand curl rule, aka cool physics sign, gangsters, with a loop. So again, your thumb is in the direction of the current, and your fingers will represent the direction of the field lines. And we'll talk about this B value and in our next lesson. That's talking about the strength of the magnetic field. Now, this is a fancied up, I guess, version of a loop. And again, if we follow our current all the way around the loop, we'll still get the same direction as they've got there, but they've just included a lot more field lines. A solenoid. A solenoid is a piece of metal that's wrapped around a cylinder, and basically it's a cylindrical core, or it's usually a copper wire. There's a heap of them in our lab. It can be considered a series of loops all stuck together, and basically the magnetic field in the middle of the solenoid is the sum of all the magnetic fields created by each loop, so they add together. And the other thing, it kind of acts like a big bar magnet, so our field lines will again go from north to south, just like they would in a bar magnet, but they also go straight through the middle of the solenoid, and we'll actually have a bit of a look at those in class. That's all for today. So in our next lesson, we'll have a bit of a play with some magnets and practice drawing some field lines, and I hope you enjoyed it, and we will have a chat about any questions that you have in class. Alright, I'll see you then. Bye.